We're going to start our chapter on nuclear physics with just the very basic properties of the nucleus. And when we're talking about the nucleus, we understand the history behind it. It was Rutherford and Geiger's experiment, where they bombarded gold foil with alpha particles. That they discovered that instead of this perhaps mushy sphere of positive charge with electrons embedded in it, what they called the plum pudding model, it was actually a very dense nucleus at the center. And Rutherford sort of viewed the atom as being similar to our solar system, where the nucleus represented most of the mass of the atom, just like the sun represented the central body of the solar system with most of the mass. He viewed that the electrons would orbit the nucleus due to the electrostatic interaction. But in any case, we do know with the advent of quantum mechanics, things are a little bit more complicated than that. And we will go into some of the quantum nature of the nucleus, but we're just going to, again, start with the very initial properties of the nucleus, the very fundamental properties of the nucleus, before we talk about its behavior and what its behavior is due to. So starting out, we first of all need to define a few basic properties that we all learn in introductory physical science. And of course, we know in chemistry, the most important of these properties is the number of protons, because the number of protons is going to determine the chemical activity, or how a particular element is going to behave and bond with other elements. So the atomic number Z equals the number of protons in the nucleus, and basically defines what element that we're dealing with. All hydrogen has 1 proton. All helium has 2 protons. Lithium, 3 protons. Carbon, 6 protons. So Z defines the number of protons and therefore how it's going to chemically interact with other elements. The number of neutrons is a number that we don't normally refer to. N, number of neutrons, is usually implied by taking the atomic number, Z, and adding it to the neutron numbers to come up with the mass number, A. Sometimes we call this the atomic mass. I think I'm at fault at sometimes just calling the mass number the atomic mass. Obviously, the atomic or the mass of the nucleus is not exactly an integer value, but A represents really the total number of nucleons at the center of the atom. So looking at notation, again, X is the chemical symbol of the element. So hydrogen with 1 proton, we would use a symbol H. Helium with 2 protons, we'd use a symbol He. And this type of notation is somewhat redundant in that our chemical symbol is really defined by our atomic number. So many times, just because it's redundant, we'll leave out Z when we're writing down the notation for an isotope. However, the atomic mass number is important to write down when we're referring to, a particular isotope of so many nucleons. So for instance, aluminum, one of the most common isotopes of aluminum, has a mass number of 27, atomic number of 13. It's aluminum. It's always going to be 13 protons. So that when we look at the number of neutrons, it contains 14 neutrons, which is the mass number minus the atomic number. So isotopes, we use the term isotope. Isotope means the same number of protons, but obviously we have the potential of different neutrons. For the lighter elements, we normally have pretty close to a 1-to-1 type ratio between protons and neutrons. As elements get heavier and heavier, we'll see in the next section that we favor neutron-rich isotopes as Z gets larger and larger, because the electrostatic repulsion from the protons makes it more energetically favorable to add more neutrons than protons. So again, here's carbon. Carbon has a number of naturally occurring isotopes, carbon 11, carbon 12, carbon 13. Most carbon, of course, is carbon 12, but of course, the radioactive isotope carbon 14 is very, very important for determining the age of different organic matter. That's because carbon 14 is created by cosmic rays in the upper part of the atmosphere, and then incorporated into living plants, and then, of course, consumed by animals. So we can always tell when something has passed away because it stops taking in carbon 14, and because carbon 14 is not stable, it will decay over time. So again, isotopes, basically all the same element, but different neutron numbers, different atomic mass numbers. And you can see here all the different isotopes of carbon. Carbon, we'll talk about later on, is one of those magic number elements where we have a lot of isotopes, both stable and unstable isotopes for that particular element. So let's look at hydrogen. So hydrogen is one of the few elements that we actually refer to its isotopes by special names. For instance, hydrogen 1 is the only element, the only isotope without a neutron. It only has one proton. Thus, we call it hydrogen 1, atomic mass number of 1. Deuterium, deuterium, a deuteron, refers to two particles, a proton and a neutron. So we'd write that as H and then superscript 2. And then tritium tri for 3, 1 proton and 2 neutrons. Hydrogen and deuterium, again, usually we refer to hydrogen 1 as just hydrogen. Deuterium is the isotope of hydrogen with 1 neutron. It's actually stable. Tritium is not. Tritium does decay and is a very important element because tritium is used in our attempts to nuclear fusion, to create nuclear fusion. Sorry about that. Create nuclear fusion in both inertial confinement and in magnetic confinement reactors. Hydrogen, its abundance, it's one of the, primordial elements, if you will. It was created first, soon after the beginning of the universe. And essentially, the universe was very, very hot. We'll talk about this in the next chapter. And an extremely high density, and was one big nuclear reactor. And during this earlier phase, the 1 proton reacted to produce deuterium and eventually helium-3. We fused together deuterium and hydrogen-1, and we will get tritium eventually decaying into helium-3. I should really look at all the different pathways, but basically, at the very, very high temperatures, you have these different isotopes which were favored. And one of the isotopes that was favored, of course, is helium-4, which is also very common. So before all the other objects in the universe, such as stars, started producing our heavier elements, the universe itself as a giant reactor, converted about 25% of all the hydrogen into helium. So again, deuterium and tritium, these isotopes of hydrogen are very, very important because we think that it will be the fuel of the future. It will be the fuel to perhaps run tokamaks, which are magnetically confined, very, very hot plasma, and allow fusion to take place, or for inertial confinement, where we fire lasers onto fuel pellets. These fuel pellets of deuterium and tritium also release massive amounts of energy when they're superheated and the fusion reactions take place. Again, other important isotopes, helium-3 is also thought to be possibly used for nuclear fusion. It's a very uncommon isotope of helium. Most helium that we have on Earth actually comes from radioactive decay. It comes from alpha particles, which we'll talk a lot about next. Nitrogen, most of the nitrogen in the air, because air is mostly made out of nitrogen, is nitrogen-14. There's a small amount of nitrogen-15. Oxygen, primary isotope there is oxygen-16, but there's also smaller quantities of oxygen-17 and 18. And of course, when we get into fission later on, we will learn that the important isotope for fission is, of course, uranium-235, but the most common isotope that we find in nature of uranium is uranium-238, which can be used to create plutonium. Obviously, we look at the charge of the nucleus as being very, very important. The charge of the nucleus is responsible for binding the electrons around it. The proton has an equal and opposite charge to the electron. The elementary charge is 1.602177733 times 10 to the minus 19 coulombs. And that is the charge of each proton. The neutron has no charge. The individual quarks do have partial charges, but the neutron itself is neutrally charged. Now, in terms of mass, when we're talking about mass, these particles are so incredibly light. Again, the proton, about 1.6 times 10 minus 27 kilograms. Because it's such a small number, oftentimes we'll use different units. Called the unified mass unit. We use U to express that, but we've actually started replacing this with the term Dalton, or the unit name Dalton, which is the same thing, but it is to give Dalton credit for his discovery of the atom. Again, this unit is based on an important property of carbon-12, its mass. Basically, carbon-12 has to be exactly equal to 12 unified mass units, or 12 Daltons. Mass can also be expressed by mega electron volts per speed of light squared equals mc squared. So if we were to convert all the energy from, let's say, a proton, which is a little bit heavier than 1 Dalton or 1 U, convert all that into energy, you get 931.494 mega electron volts. Okay. So basically, if you want the total mass energy of carbon-12, you can take 931.494 mega electron volts, multiply it by 12, and you'd have the amount of energy released if you could convert all of the carbon-12 nucleus into a pure energy. Now, let's talk about the size, because I think we don't appreciate how small the nucleus really is and how shocked Rutherford and Geiger were when they got their scattering results back. Typically, when we talk about the wavelength of light, we're talking, fractions of a micrometer, a micron, okay, or maybe hundreds of nanometers. All right. When we talk about the size of the atom, we're typically talking about a fraction of a nanometer or in hundreds of picometers. When we talk about a nucleus, we actually have to go in an even smaller scale. We've got to go 3 orders of magnitude smaller than pico, which means we're going 5 orders of magnitude smaller than the size of the atom itself. So the nucleus is about 100,000 times, in linear dimensions, smaller than the atom. The volume, of course, if we take 10 to the 5th, because that's 10 to the 5th times smaller, volume goes by the radius cubed. The volume of the nucleus is basically 10 to the minus 15 in terms of the fractional volume of the total atom. So nuclei are typically measured in femtometers. More commonly, we usually use the unit called the Fermi, named after Enrico Fermi. And nuclei tend to be spherical in shape. However, some are ellipsoidal if they have a very large spin. The nucleus is usually represented by a bunch of hard spheres, plastered together, but it is, truly on the quantum mechanical scale. When we look at the de Broglie wavelength of the protons and neutrons, they are definitely scattered, I should say, spread over a volume. Okay, obviously we can't see it directly, and in order to see them, we have to scatter other particles off of them. But if we could visualize the wave function for the protons and neutrons, it would appear to be, this sort of fuzzy blob, if you will. The smallest nucleus, obviously, is going to be hydrogen. And to say it's 2 Fermis is probably a little bit hard to justify, because there's been a lot of controversy with regard to how large the proton really is. In terms of other, size of nuclei, again, they're typically measured in terms of Fermis. Okay, so really some of the largest nuclei going to like uranium-235, 258. I say 250. Why does that not seem right? Did I really do that? Uranium-238. Okay, I did do that. It's uranium-238, folks. So I apologize for that. Uranium-238 is one of the largest nuclei at 15 Fermis, and the other transuranic elements aren't going to be much larger with regard to their nuclei. Sorry about that diagram. So again, you put the nucleus next to the atom. We're talking about really, 10 to the 5 cubed, a volume difference of, 10 to the 5. That would be, says there a trillion times. Trillion is 10 to the 12. It'd be 1,000 trillion times smaller in volume. Okay, so let's do some calculations here. And because nuclei are spheres, because nuclei are made of nucleons, which are fermions, where they don't like to overlap their wave functions, we can basically say that the radius of a nucleus is equal to some constant R0, which would probably represent the approximate radius of each of the nucleons, times a to the 1/3 power. Where does this come from? Well, if you think about this, the volume of a sphere is 4/3 pi r cubed. So every time I add a nucleon, it adds volume. So the volume is proportional to the radius cubed. The radius is therefore proportional to the cube root of the volume. The cube root of the volume, I should say, the volume is proportional to how many nucleons I try to put in that nucleus. And again, just to emphasize this, I have represented the nucleus as this collection of hard spheres, cemented together. That's not reality. Again, these, particles are, much like the electrons are in their orbits. They occupy a indeterminate space, and the only way that we're able to get their locations is to bombard the nucleus with very energetic particles. So again, this is more of it's like a classical picture of the nucleus. So just looking at the nucleus, obviously, because it occupies such a small volume compared to the atom, we're going to come up with a really, really large density when we try to calculate the density based on the radius. And really, looking at this equation, we can basically see that nuclear matter pretty much all has the same density. So let's do the radius of iron 56. This is the most common isotope of iron. And in terms of binding energy, it has one of the largest binding energies of all the nuclei. Iron is element 26. So Z is equal to 26. That's the number of protons, 26 protons. And given that it's element 56, there would be 30 neutrons. 56 minus 26, the atomic mass number minus the atomic number gives you the number of neutrons. So, the number of neutrons, the number of protons isn't what's important here. It's the atomic mass number. So first we calculate the radius. Again, I have our constant 1.2 times 10 to the minus 15 meters. I multiply that times the cube root of 56. Remember, the cube root is just raising the number to the 1/3 power. Cube root of 56 is 3.82. So we get a iron nucleus, which is 4.6 times 10 to the minus 15 meters, 4.6 Fermis in radius, almost a little more than 9 Fermis in diameter. The volume of iron 56, again, we already stated that the volume of a sphere, and we're going to assume that iron is a spherical nucleus. That's been confirmed by experiment. It's 4/3 pi r cubed. Throw in that radius, and we get that the volume is 4 times 10 to the minus 43 meters cubed. Okay, so we know density is equal to mass divided by volume. We're just going to put the two together. The mass of iron 56 is 55.9 Daltons, if you will, or universal mass units. And we multiply this times 1.66 times 10 to the minus 27 kilograms per U. That gives us a mass of 9.3 times 10 to the minus 26 kilograms. Mass divided by volume gives me density. Putting things in perspective, water has a density of 1 gram per cubic centimeter, or 1,000 kilograms per cubic meter. So that's comparing to 10 to the 3. This has 2.4 times 10 to the 14. Okay, that's 230 trillion times more dense than water. Okay, so the density of nuclear matter is very, very high. I think the density of a neutron star is, between 4 and 5 times 10 to the 17 kilograms per meter cubed. A neutron star is the densest object in the universe without becoming a singularity, without becoming a black hole. So again, in terms of nuclear matter, its density is very, 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 very high. And when we look at a neutron star, we're looking at it's not a complete ball of neutrons. Rather, it's very, very heavy nuclei, which are squeezed together, at least on the surface. And then as we go deeper, models seem to indicate that the neutrons and other exotic particles become free, but basically just a lot of nucleons placed in a very, very tight space. Now, the reason why a neutron star is going to be slightly more dense than the nucleus of an atom is because the nucleus of an atom, the confining force, is the strong force that's pulling everything together. With a neutron star, you have, yes, a strong force, which is causing an interaction between nucleons, but gravity becomes a very, very dominant force in that particular case. And in fact, there's an even third force called a degeneracy force, which is trying to keep the neutrons and protons from merging together. Once that happens, you're pretty much on your way to collapsing into a black hole. But again, that is sort of an overview of the basic properties of the nucleus in terms of atomic number, neutron number, atomic mass number, how large it is in terms of radius, how much volume, and again, finally, the mass and density.